Hi everybody, welcome to this video about partial fraction decomposition. Suppose we have an output signal written in the S domain, in the Laplace domain, with a function like this. And that output signal C is an outcome of an input signal multiplied with a transfer function. So we have an expression in the S domain, but we want to translate that to the time domain because we want to know how the function really looks in my time domain. So we have to translate that back towards the time domain, but we can't do it directly. So what we are going to do is we are going to apply partial fraction decomposition. So the approach is we are going to bring this denominator back to 2 times a denominator which we know and which we can directly transfer to the time domain by using the inverse Laplace transformation. So what we are going to do is we split this denominator and we split them up in two parts. One part with s in the denominator and another fraction with s plus 5 in the denominator. What we do not know is what the expression, what the constant value will be in the numerator of both fractions. So we have to calculate that. So first of all, we transform this transfer function, or this output signal, I should say, in the S domain back to a constant a over s and another constant b over s plus 5. And when we have solved a and b, well, we can use the inverse Laplace transformation table, look it up, what the time functions of these expressions will be, and then we know c in the time domain. So how do we calculate a and b? What we are going to do is we are going to transform these denominators of the separated fractions back to the denominator which we had over here. So when we have to calculate this denominator back to that one, we have to multiply s by s plus 5 because s times s plus 5 is in the original denominator. But when we apply this in the denominator, we should also multiply the numerator by s plus 5 in order to get an equal fraction like this one over here. So we multiply s plus 5 in the denominator and s plus 5 in the numerator. To transform this denominator back to the original one, we have to multiply s plus 5 by s over here, but we have to do the same thing in the numerator of this fraction. So we multiply b times s and the denominator s plus 5 also by s. And now we have two fractions with denominators which are equal to the original one, and we may add the numerators of both fractions, and then we get a new fraction, one fraction with the denominator which is equal to the original one, and the numerator is a times s plus 5 plus b times s. So we could write that in another way. We could say is 5 times a, which is the constant value of this numerator, and we have a times s plus b times s, which equal a plus b times s. So we have a new fraction with the same denominator as over here, and when these two fractions should be equal to each other, then also the numerators of both parts should be the same. So we can say 5 times a, which is the constant value in this numerator, should be equal to this numerator, which is equal to 2. And also the parts multiplied with s, so a plus b times s over here should be equal to 1 times s over here. So a plus b should be equal to 1. So now we have two expressions and two unknown values, so we can solve a and b. So this is an easy one. 5 times a is 2, so a is 2 over 5, which is equal to 0.4. When we know a, we can also calculate b, because b is 1 minus a, so b is 1 minus a, 1 minus 0.4, which is equal to 0.6. So now we have solved a and b. So now we have a new expression in the S domain for the output signal, which says that C is equal to 0.4 over S plus 0.6 over s plus 5. So it's this expression. We could also write it somewhat in another way. It's 0.4 over s plus 0.6 times 1 over s plus 5. And these separate parts can be transferred easily to the time domain by using the inverse Laplace transformation rule. Well, 1 over s is in the time domain 1 multiplied with zero point 0.4 equals 0.4. So that's this value. 1 over s plus 5, well, in the Laplace transformation table, it says 1 over s plus a equals a time domain function, which is equal to e to the power minus a times t. So that a is 5 over here. So 1 over s plus 5 is in the time domain e to the power minus 5 times t multiplied by this constant 0.6. So this part yields this part. So now I have my function in the time domain, so I know how this signal looks like in the time domain. So summarize, what we are going to do is we always start with the output signal in the S domain, so it's just the transfer function of the system multiplied with the input signal. We start off with partial fraction decomposition, so we split the denominator up in separate parts. Then we calculate A and B. So in this example, this was A and B. So this is my signal in the S domain. And then we apply the inverse Laplace transform, which yields this function in the time domain. That was the approach for an easy function with only easy denominators over here. We're going to look into two exceptions. We start off with an equation which looks like this. Well, don't be scared. Yeah, it's really a tricky one. It's a big expression, but we are going to solve it. What we're going to do is um, we look to this expression. When you have a quadratic function in your denominator, you always have to split that up, and one part with a quadratic function in it, and in one part with a power which is one lower. So we have s plus 1 squared over here, which gives me one part which is equal to this part s plus 1 squared, and we have a part with s plus 1 and then 1 power lower, so to the power 2 minus 1, so to the power 1. So it equals s plus 1. And that both times a constant which we do not know. So that is this part. When you have a part in the denominator which says it's equal to s squared plus a constant value, and you look to the inverse Laplace transformation table, you see that there are two time functions which have this kind of function, which is a cosine function and a sine function. So this part yields something with a cosine, c times a cosine function, and a cosine function in the S domain is s over s squared plus 4, and we have something with a sine function, and the sine function of the sine function which has this in the denominator yields 2 over s squared plus 4 because when this is omega squared in the Laplace transformation table, then for the sine, here is my omega. So it's d times a sine function, in this example 2 over s squared plus 4. So now we have split that up in two parts which are coming from this part of the denominator, and two parts, a sine and a cosine, which are coming from this part of the denominator. And we have four unknown values, a, b, c, and d. First step, what we are going to do now is we multiply all fractions back to the original fraction over here. So let's do it. We have the fraction over here, which is s plus 1 squared. But the original fraction is s plus 1 squared times s squared plus 4. So we have to multiply denominator and numerator by this part of the expression, s squared plus 4. So we do it here and we do it in the numerator. When we have this part and we want to bring it back to the original one, we have to multiply it by s plus 1, so then we get s plus 1 squared, and multiply it by s squared plus 4. So we have to multiply it with s plus 1 times s squared plus 4. So we have to do it in both the numerator again and in the denominator. And we have the constant b over here, of course. Then we have the part with the c, and we are also bringing this part back to the original denominator, so we have to multiply s squared plus 4 times s plus 1 squared in the numerator and denominator. We do that over here. And of course, we have to do it again for the part with the d value. We have to bring also this back to the original denominator. So we multiply it by s plus 1 squared over here. So also the numerator is multiplied by s plus 1 squared. So now we have four fractions with the same denominator, which equals the original denominator over here. And because all these four fractions have the same denominator, we can put these under this fraction, and we may add all the numerators. So we get a numerator which is equal to a times s squared plus 4 plus b times s plus 1 times s squared plus 4, which is written over here, plus c times s plus 1 squared over here, plus d times 2 times s plus 1 squared over here. And we can switch, of course, the 2 times d times 2 by 2 times d. And that numerator of this part should be equal to this numerator over here. So 5 times s squared plus 70. So when these parts should be equal, then all parts in the left side of the equation with s to the power 3 should be equal to all parts with s to the power 3 on the right side of the equation. All parts with s squared on the left side of the equation should be equal to the parts with s squared on the right side of the equation. That should also be the case for the parts with s on the left side of the equation should be equal to the parts with s on the right side of the equation, and all constants to the left side of the equation should be equal to the constants at the right side of the equation. So for first thing what we are going to do now is we work that out, and when we do that we get this part will be a times s squared plus 4 times a. This part yields b times s to the power of 3 plus b times s squared, b times 1 times s squared, plus 4 times b times s plus 1 times 4 times b is 4b. This yields c times s squared is c times s to the power of 3 plus 2 times s times cs is 2 times c times s squared plus 1 times cs is 1 times cs over here. This yields 2 times d times s squared plus 4 times d times s plus 2 times d, and that all should be the same at the right side of the equation, which is 5 times s squared plus 70. So first of all, let's have a look to the parts with s to the power of 3 to the left side of the equation and the right side of the equation. I made them red. So we have at the left side of the equation b times s squared, s to the power of 3, so b times s to the power of 3 plus c times s to the power of 3. And there's 0 times s to the power of 3 at the right side of the equation. So b plus c, parts with s to the power of 3, is equal to 0, because there are 0 parts with s to the power of 3 at the right side of the equation. So b plus c equals 0, so we could also say b equals minus c. We do the same for the parts with s squared. We have a times s squared, b times s squared, 2 times c times s squared, plus 2 times d times s squared. So a plus b plus 2 times c plus 2 times d are equal to 5. So that is written over here. Well, we notice that b is minus c, so we can fill that in over here. Then we get a plus minus c plus 2 times c plus 2 times d is 5, so we get a plus c plus 2 times is equal to 5. Now let's do the same thing with the parts which have a s in the fraction, or in the part of the equation. So we have 4 times b times s over here, c times s over here, and 4 times d times s over here. And here we have 0 times s. So 4b plus c plus 4 times d is equal to 0. Well, we can we can replace beta with minus c, so we get minus 4b, 4 times b equals minus 4c plus c, which is equal to minus 3 times c plus 4 times d is 0. So we could also say 4d is 3 times c, or d is 3 over 4 times c. When we fill that in that expression, we have a plus c plus 2 times d, which is 1.5 times c, which is equal to 5. Let's call that equation number 1. And now we are doing the last thing. We compare the constant values of the left side of this equation with the constant parts at the right side of the equation. And then we see that 4 times a plus 4 times b plus 2 times d equals 70. So that is this expression. Well, we can replace b with minus c over here, and we can replace d with this expression 3 over 4 times c over here, and then we get 4 times a minus 4 times c plus 1.5 times c is equal to 70. And let's call that equation number 2. So we now have two equations with two unknown values. These two equations, number 1 and number 2, number 1 says a plus c plus 1.45 times c equals 5. So a plus 2 times 5, 2.5 times c equals 5. And we have 4 times a minus 4 times c plus 1.5 times c, which equals 4 times a minus 2.5 times c, which equals 70. Two equations, two unknown values, so we can solve a and c. And when we have c, we can calculate b, and when we have c, we can calculate d. And then we have all the constant values a, b, c, and d. Well, the easy one is to solve a from these two expressions by adding these up. Then we get a plus 4 times a is 5 times a. We have 2.5 times c minus 2.5 times c, so that is ruled out. So then we have to add up the right parts of the equation, which is 5 plus 70. So we get 5 times a is equal to 75, which yields a is 15. Well, when we have a, we can calculate c. We can fill it in, for instance, over here, and we can calculate c, and that gives us the value for c. C is minus 4. When we have c, we can calculate b. B is 4, and we can calculate d over here, which is minus 3. So now we have the expression. This was my original signal description in the S domain. We split that up in several fractions, and we solved a, b, c, and d. A was 15, b was 4, c was minus 4, and d was minus 3. And now we can transform this part, that part, that part, and that part back to the time domain by using the inverse Laplace transformation. Well, when you look to the Laplace transform table, you see that 1 over s squared um, equals a function in time domain which is equal to t. But when you have s plus something, a constant squared, you have to apply the shifting rule. So we have to multiply that function t with the shifting rule, which says that it has to be multiplied in time domain by e to the power minus a times t, and this is the value for e. So this yields t times e to the power minus t, and we have to multiply that with 15. So that is this expression, 15 times t times e to the power minus t. Well, this is an easy one, s to the power, 1 over s plus 1 yields in the time domain e to the power minus t multiplied with 4 is 4 times e to the power minus t. This is a cosine, the cosine of 2 times t multiplied with minus 4, and this is the sine of 2 times t multiplied with minus 3. And this value for the time domain expression is only valid from t is 0. That was also the case by the first example. So it is always valid from t is 0. So that's all about partial fraction decomposition. Thank you for watching.